Ladies and gentlemen, there's a hidden switch inside you, a biological pathway that governs how calm you feel, how focused you stay, and even how easily your brain learns. That switch is called the vagus nerve, and today you're going to learn how to control it. The vagus nerve is the longest cranial nerve in your body, running from your brainstem down to your heart, lungs, and gut. It's the main highway connecting your thoughts to your organs, your emotions to your breath, and your stress to your heartbeat. But here's the truth. Most people let it run on autopilot. They live at the mercy of stress. They wake up anxious, stay wired all day, and wonder why they can't focus, sleep, or feel happy. That ends now. You can take control, starting with your breath. One of the most powerful discoveries in neuroscience is your breath is a tool, not just a reflex. When you take a long exhale, you signal the vagus nerve to activate the parasympathetic nervous system, the part responsible for calm, clarity, and healing. Just one physiological sigh. 2 inhales, 1 long exhale can change your state in seconds. But that's just the beginning. Want to increase alertness without caffeine? Train your vagus nerve. Want to feel happier without a pill? Train your vagus nerve. Want your brain to learn faster and adapt more easily? Train your vagus nerve. How? You can start with daily cold exposure. Even 30 seconds under cold water trains your nervous system to tolerate discomfort and builds resilience. You can also hum, chant, or meditate. All ancient techniques now proven to stimulate vagal tone. Because here's the secret to neuroplasticity: your brain changes when your body feels safe. And the vagus nerve is the gatekeeper of that safety signal. You don't need to buy expensive devices. You don't need to wait until you feel better to act. You just need to begin right now, today, with your next breath. So I challenge you, master the state of your nervous system. Because when you control the vagus nerve, you don't just calm your body. You awaken your mind, you sharpen your focus, you become unstoppable. Thank you. The vagus nerve is one of the most vital components of the human nervous system, often referred to as the wandering nerve due to its extensive reach throughout the body. Originating from the brainstem, it travels down the neck, branching out to the throat, heart, lungs, diaphragm, digestive organs, and even the kidneys. Its vast network is responsible for a two-way communication channel between the brain and the body. What makes it extraordinary is that it doesn't merely send commands from the brain downward. It also relays critical information from the body back up to the brain. This dynamic feedback loop plays a foundational role in maintaining internal balance, or what science calls homeostasis. It regulates crucial functions such as heart rate, digestion, respiratory rate, immune response, and even vocal tone. It oversees the parasympathetic branch of the autonomic nervous system, which is responsible for rest and digest functions. When active, it slows the heart rate, lowers blood pressure, promotes deeper breathing, enhances nutrient absorption, and reduces inflammation. These are not minor effects. These are the bedrock of long-term physical and mental health. The vagus nerve is also intricately tied to our emotional and psychological well-being. It influences how we feel, how we interpret stress, and how quickly we can recover from emotional upset. For instance, when we experience anxiety, panic, or fear, it is the vagus nerve that either helps bring us back to calm or leaves us stuck in a loop of overactivation. The strength of this nerve, often referred to as vagal tone, can be measured through heart rate variability, HRV, a powerful marker of resilience and adaptability in both body and mind. Beyond mood and physical regulation, the vagus nerve plays a surprising role in social connection. It affects our facial expressions, voice modulation, and ability to interpret the emotions of others. This is why people with high vagal tone often appear more emotionally attuned and socially engaged. Conversely, when vagal tone is weak, individuals may struggle with emotional regulation, communication, and empathy. What's even more fascinating is the growing body of research showing that the vagus nerve plays a key role in neuroplasticity, the brain's ability to rewire itself, learn new information, and adapt to new experiences. Stimulation of the vagus nerve, whether through breathwork, cold exposure, meditation, or even direct clinical techniques like vagus nerve stimulation, VNS, can increase the release of neurotransmitters such as acetylcholine and norepinephrine. These chemicals are essential for attention, memory, and brain plasticity. In times of crisis or trauma, the vagus nerve helps determine whether we fight, flee, freeze, or recover. It acts as a switchboard that governs our physiological responses to the world around us. When functioning optimally, it supports a seamless transition between heightened alertness and deep relaxation, enabling us to face challenges and return to baseline quickly. This rapid regulation is essential not just for mental health, but also for performance, learning, and longevity. The vagus nerve is also deeply influenced by our behaviors. What we eat, How we breathe, how we sleep, and even the way we speak and interact with others can all influence its tone. This means that the mind-body connection is not just a metaphor. It's a literal, measurable, physiological reality with the vagus nerve acting as the primary conduit. From the rhythm of your heartbeat to the tone of your inner dialogue, from the calmness of your breath to the flexibility of your mind, the vagus nerve silently orchestrates the balance between your internal and external worlds. It is the thread that weaves together emotion, cognition, health, and resilience, functioning not as a background player, but as a central axis in your daily experience. Breath is one of the few bodily functions that is both involuntary and voluntary, meaning it happens automatically, but we can also take conscious control over it. This unique quality makes breathing a powerful tool for influencing the state of the nervous system. When we breathe in certain ways, we can directly shift our physiology from stress to calm, from lethargy to alertness, from chaos to focus. The reason for this is the deep integration between the respiratory system and the autonomic nervous system, particularly through the vagus nerve. Every breath we take sends signals to the brain about the state of our internal and external environments. Shallow, rapid breathing, common during stress and anxiety, sends danger signals to the brain, activating the sympathetic nervous system, the fight or flight response. In contrast, slow, deep breathing, especially with a prolonged exhalation, signals safety, engaging the parasympathetic nervous system via the vagus nerve and inducing a state of calm and relaxation. The length and rhythm of the breath acts inputs to the brain, guiding the release of neurochemicals that govern our alertness, mood, and emotional regulation. For example, short, fast breaths can increase levels of cortisol and adrenaline, while slower breaths with longer exhalations help release acetylcholine, a neurotransmitter linked to calmness, focus, and neuroplasticity. One of the most scientifically supported techniques is the physiological sigh, a double inhale followed by a long exhale, which has been shown to reduce stress in real time by rebalancing carbon dioxide and oxygen levels and activating vagal tone. Such breathing patterns are not merely calming, they are regulating at a core neurological level. Moreover, specific breathing practices can alter brainwave activity. Slow nasal breathing can increase alpha wave activity, associated with a relaxed yet alert state, while also improving the coupling between brain regions involved in attention and emotional regulation. Breath is also deeply connected to heart rate variability, HRV. A marker of the flexibility and adaptability of the nervous system. When we breathe in, heart rate slightly increases. When we exhale, it slightly decreases. The more this rhythm fluctuates in a healthy range, the more resilient the nervous system becomes. This rhythmic modulation, known as respiratory sinus arrhythmia, is enhanced by conscious breathwork and is one of the clearest signs of vagal tone and autonomic balance. Breathwork has also been shown to influence the default mode network MDMN, a set of brain regions associated with mind wandering and self-referential thought. Overactivity of the DMN is linked with anxiety, rumination, and depression. Conscious breathing, especially through techniques like box breathing, alternate nostril breathing, or current breathing, can quit the DMN and shift activity toward networks responsible for attention presence and task execution. This has profound implications not just for stress management, but also for improving learning, memory, and mental performance. In clinical settings, breath-based interventions are being increasingly used to treat conditions like PTSD, generalized anxiety disorder, panic attacks, and even chronic inflammatory diseases. This is because breath not only changes brain, but also affects the immune system through the vagus regulation of inflammatory responses. Breathing in specific patterns can lower levels of pro-inflammatory cytokines, thus reducing the physiological burden of chronic stress and illness. This physiological impact, achieved through something as simple and accessible as breath, highlights the extraordinary power of this everyday function. Breathing through the nose rather than the mouth offers additional benefits. Nasal breathing helps filter, humidify, and regulate the temperature of incoming air. And it also facilitates nitric oxide production, a molecule that improves oxygen uptake, boosts circulation, and has antimicrobial properties. This small shift in breathing method can have a significant cumulative impact on energy levels, cognitive function, and immune defense. Furthermore, breath is a bridge between conscious thought and unconscious processes. By choosing how to breathe, we influence systems that are otherwise outside of our conscious control, including hormone release, digestive function, and emotional reactivity. Because of this unique leverage point, breath is often the first gateway into practices like meditation and mindfulness. It offers an immediate anchor to the present moment, bypassing the racing mind and grounding attention in the body. This sensory feedback loop, established through breath awareness, helps develop interoception, the brain's ability to sense internal states, which is essential for emotional intelligence and behavioral self-regulation. When practiced consistently, breathwork enhances the capacity to pause, reflect, and choose responses instead of reacting impulsively. It creates a spaciousness in the mind that allows for clarity, creativity, and better decision-making. Mood and alertness are often viewed as purely psychological experiences tied to thoughts, emotions, or external events. However, a deeper understanding of human biology reveals that these states are profoundly rooted in physiology. The way we feel emotionally, whether calm, anxious, focused, or fatigued, is intimately linked with the functioning of our nervous system, the balance of our hormones, the rhythms of our heart and breath, and even the state of our gut. Mood and alertness are emergent properties of the body's internal systems working or failing to work in harmony. They are shaped by the neurochemical environment of the brain. The level of inflammation in the body, and the tone, the vagus nerve, which serves as the communication superhighway between brain and body. At the heart of mood regulation is the interplay between neurotransmitters such as serotonin, dopamine, norepinephrine, and GABA. These chemical messengers are not simply created in the brain in response to thoughts or external stimuli. They are constantly being influenced by physical factors such as sleep quality, nutrient availability, gut microbiota, blood sugar levels, and inflammation. For example, over 90% of the body's serotonin is produced in the gut, and its availability in the brain is dependent on the health and permeability of the gut lining, as well as the presence of certain gut bacteria. This gut-brain axis highlights how digestion, diet, and even intestinal inflammation can directly affect emotional states, making mood far more than a mental issue. It is a whole body experience. Similarly, alertness is not just the result of mental motivation or willpower. It's the product of a well-regulated arousal system involving the brainstem, thalamus, and the release of stimulating neurochemicals like norepinephrine and acetylcholine. These chemicals drive our capacity to focus, stay awake, and process sensory input effectively. Their production and regulation are influenced by circadian rhythms, light exposure, breathing patterns, and overall vagal tone. For example, exposure to natural light in the morning increases cortisol and suppresses melatonin, creating a natural boost in alertness. The autonomic nervous system also plays a major role, as a dominant sympathetic state can induce hypervigilance and anxiety, while excessive parasympathetic dominance may lead to fatigue and mental fog. The balance between these states creates the optimal condition for calm yet alert focus. In stressful conditions, the body enters a fight or flight mode, releasing cortisol and adrenaline, increasing heart rate, and preparing the body for action. This is not inherently bad. In fact, short-term stress can sharpen alertness and aid performance. But when this state becomes chronic, it disrupts the delicate balance of brain chemicals and hormonal rhythms that support stable mood and consistent energy. Chronic stress reduces dopamine sensitivity, depletes serotonin, increases systemic inflammation, and impairs the feedback mechanisms of hypothalamic pituitary adrenal HPA axis. This physiological chaos then manifests as anxiety, depression, irritability, and brain fog, showing that these experiences are not just mental, they are biologically rooted in systemic dysregulation. Moreover, mood is affected by heart rate variability HRV/V8, which reflects the adaptability of the autonomic nervous system. Low HRV is associated with mood disorders, while high HRV is linked to resilience, emotional regulation, and a greater ability to shift between mental states. Practices that increase vagal tone, such as slow breathing, cold exposure, meditation, and physical activity, can enhance RV, thereby improving the physiological basis for emotional stability and cognitive flexibility. This suggests that interventions aimed at improving physiology can be just as effective, if not more so, than purely cognitive or behavioral strategies in shifting one's mental state. Hormonal rhythms also play a significant role in modulating mood and alertness. The daily oscillation of cortisol, a hormone often mischaracterized as purely negative, is essential for maintaining energy and cognitive performance. Cortisol peaks in the early morning to promote wakefulness and gradually tapers throughout the day. Disruption of this rhythm through irregular sleep, artificial light exposure, or chronic stress leads to flattening of the cortisol curve, resulting in fatigue, depression, and reduced alertness. Similarly, hormones like estrogen, progesterone, testosterone, and insulin influence neurotransmitter levels and brain function, and their imbalances can lead to mood instability, low motivation, and attentional deficits. Even posture and physical movement influence physiological states that affect mood and alertness. Physical inactivity, poor posture, and shallow breathing contribute to reduced blood flow to the brain, lower energy levels, and increased rumination or lethargy. In contrast, movement increases circulation, enhances oxygen delivery, and stimulates the production of brain-derived neurotrophic factor BDNF-FNF, a protein essential for neuroplasticity and mood regulation. The act of moving, stretching, or engaging in physical activity is not just beneficial for the body, it directly stimulates the neurobiological processes that support a positive and focused mental state. Sleep is another critical factor linking physiology to mood and alertness. Sleep regulates the glymphatic system, which clears metabolic waste from the brain and plays a crucial role in memory consolidation, emotional processing, and hormonal regulation. Poor sleep impairs glucose metabolism, increases inflammation, and alters the expression of genes related to mood and immune function. A single night of disrupted sleep can decrease dopamine receptor sensitivity, making pleasurable experiences feel dull and increasing susceptibility to negative thoughts and emotional reactivity. This connection reinforces the understanding that emotional resilience and mental clarity are not traits we summon at will. They emerge from physiological conditions that must be cultivated and protected. Neuroplasticity, the brain's remarkable ability to rewire itself in response to experiences, learning, and environmental input, is not a process that occurs in a vacuum. It depends heavily on the state of the nervous system. For the brain to form new neural connections, strengthen existing ones, or prune away inefficient pathways, it must be in an optimal physiological and emotional state. This means that the autonomic nervous system, especially the balance between the sympathetic fight or flight and parasympathetic rest and digest branches, plays a foundational role in determining whether or not neuroplasticity can take place. The nervous system acts as a gatekeeper when we are under chronic stress. In a hyperaroused or dysregulated state, the brain deprioritizes learning, reflection, and adaptation, focusing instead on immediate survival. In contrast, when the nervous system is well regulated, oscillating between activation and recovery, it creates the ideal internal environment for lasting changes in neural architecture. The neuroplastic process is energetically demanding, requiring metabolic resources, a well-regulated hormonal landscape, and a state of focused attention paired with periods of deep rest. Cortisol and norepinephrine, both released during heightened states of arousal, can support plasticity when elevated in short, intentional bursts, such as during challenging learning or focused effort. However, when these stress chemicals remain chronically elevated, they begin to inhibit synaptic plasticity and damage structures like the hippocampus, a key region for memory and spatial navigation. This is why traumatic or excessively stressful environments impair learning and memory. The nervous system interprets ongoing stress as a threat and, in doing so, diverts energy away from long-term adaptation in favor of short-term defense mechanisms. The right nervous system state is not one of flat calm or constant arousal, but rather a dynamic rhythm between engagement and recovery, which allows the brain to encode, process, and integrate new information. Attention is another crucial ingredient for neuroplasticity, and attention itself is governed by the state of the nervous system. A brain in a distracted, overstimulated, or fatigued state struggles to direct sustained attention toward a stimulus. And without attention, neuroplasticity is extremely limited. Conversely, focused attention, particularly when paired with novelty, emotional salience, or a sense of urgency, signals the brain to release neuromodulators like acetylcholine and dopamine, which tag certain synapses for strengthening. These neuromodulators function like spotlight operators, illuminating the neural pathways that need to be reinforced while leaving others untouched. Acetylcholine enhances signal-to-noise ratio at the synaptic level, allowing for clearer encoding of important information, while dopamine provides the motivational drive that sustains effort and reinforces reward-based learning. But these chemicals are released effectively only when the nervous system is tuned to a precise balance. Not too sluggish, not too stressed. After the period of intense focus or learning, the nervous system must shift into a more relaxed parasympathetic state to allow for consolidation. It is during this offline phase, often involving deep rest, sleep, or non-task-oriented states like daydreaming, that the brain replays patterns of neural activity, strengthens newly formed circuits, and refines connections based on relevance and utility. This integration phase is just as important as the period of effortful learning, and without it, the gains made during focused work are often lost. Sleep, in particular, plays a vital role here. During slow, wave, and REM sleep, the brain engages in spontaneous reactivation of neural ensembles formed during wakefulness, a process that strengthens memory and facilitates structural change in the cortex. Disrupted or inadequate sleep interferes with these processes and reduces the brain's overall capacity for plasticity. Another key component is safety. The brain becomes plastic when it feels safe, both physically and emotionally. The sense of safety is mediated through the vagus nerve, which assesses cues from the environment and internal physiology to determine whether a state of calm and openness is warranted. When vagal tone is high, the nervous system is more flexible, heart rate variability increases, and the individual becomes more capable of shifting between different states, alertness, relaxation, focus, and recovery. This flexibility supports not only emotional regulation, but also the capacity to engage in learning and adaptation. Practices that enhance vagal tone, such as controlled breathing, cold exposure, mindful movement, and even social connection, create the physiological foundation for safe, effective neuroplastic change. Environmental factors also interact with the nervous system to influence neuroplasticity. A noisy, chaotic, or emotionally volatile environment can keep the nervous system in a reactive mode, limiting the bandwidth available for learning. In contrast, structured, calm, and enriched environments provide cues of predictability and support, allowing the nervous system to relax into states where plasticity is more likely to occur. Context matters. The same brain will respond differently in two different environments. Even when presented with the same stimulus or task, a brain that feels supported and stable will be more willing to expend energy on growth, risk-taking, and creative exploration, all of which are necessary for meaningful neuroplastic change. Movement also plays a subtle yet important role in priming the nervous system for plasticity. Physical activity, particularly rhythmic aerobic movement, enhances circulation, increases brain-derived neurotrophic factor, BDNF, and stabilizes the autonomic nervous system. BDNF acts like a fertilizer for the brain, promoting the growth of new neurons, enhancing synaptic transmission, and improving the survival of newly formed connections. But BDNF is not released in isolation. It is coupled with the overall physiological state of the individual. Without the appropriate nervous system conditions, BDNF remains underexpressed, and the brain fails to enter a plastic state even in the presence of intellectual stimulation or cognitive demand. This further underscores that neuroplasticity is not a purely cognitive process. It is deeply embodied and dependent on systemic regulation. Nutrition and hydration are equally significant, as they provide the raw materials needed for neurotransmitter synthesis, myelination, and energy production. Dehydration, blood sugar instability, and nutrient deficiencies can all impair synaptic transmission and diminish the nervous system's ability to sustain the energy-intensive process of rewiring itself. Omega-3 fatty acids, for instance, are crucial for membrane fluidity and synaptic flexibility, while amino acids from protein are precursors to neurotransmitters like serotonin, dopamine, and GABA. Micronutrients such as magnesium, zinc, and B vitamins play supportive roles in enzymatic pathways involved in neuroplastic changes. The nervous system requires a steady, balanced internal environment to remain in the window of plasticity, and these physiological foundations must be in place to allow the brain to change in response to intention, effort, and experience. Cold exposure and heart rate variability, HRVR, are two of the most powerful tools available for assessing and improving the function of the autonomic nervous system, which governs the balance between stress and recovery. Cold exposure, particularly deliberate cold exposures such as cold showers, ice baths, or immersion in cold water, acts as a potent stressor that forces the body to adapt in real time. When the body is exposed to cold, it immediately activates the sympathetic nervous system, resulting in a surge of adrenaline, an increase in heart rate, and a spike in alertness. This controlled activation of the fight or flight response allows individuals to intentionally stimulate stress pathways in a safe and measured way. Over time, repeated exposure to this kind of stimulus conditions the nervous system to become more resilient, increasing the body's ability to regulate itself under pressure. This form of hormetic stress, small doses of challenge that lead to long-term adaptation, trains the nervous system to remain calm and collected even in situations that would previously trigger anxiety, panic, or dysregulation. In addition to its impact on stress resilience, cold exposure significantly enhances vagal tone, which is one of the best predictors of overall nervous system health. The vagus nerve, when stimulated through cold, especially around the face and neck, sends signals to the brain to increase parasympathetic activity. This paradoxical combination of sympathetic arousal followed by parasympathetic recovery is a key feature of cold exposure's effectiveness. It forces the nervous system to practice transitioning between activation and relaxation, strengthening its overall flexibility. This enhanced capacity to shift between states is at the core of nervous system resilience and is what enables people to handle more emotional, mental, and physical stress without becoming overwhelmed. Over time, individuals who practice regular cold exposure report increased focus, mental clarity, emotional control, and energy levels, all of which are directly tied to a better regulated autonomic nervous system. Heart rate variability, or HRV, serves as a real-time biomarker for this balance. HRV measures the variation in time between each heartbeat, and rather than being a sign of irregularity, this variability is actually a sign of nervous system health and adaptability. A high HRV indicates that the body can easily toggle between sympathetic and parasympathetic states, while a low HRV suggests rigidity, chronic stress, or overtraining. HRV is influenced by numerous factors, including sleep quality, nutrition, emotional stress, and breathing patterns, but it is also highly responsive to practices that directly impact the vagus nerve, such as cold exposure and breathwork. By tracking HRV over time, individuals can gain insights into how well their nervous system is functioning and responding to life's demands. It becomes a valuable feedback tool, showing whether stress management strategies are effective, whether recovery is adequate, and whether the body is primed for performance or in need of rest. One of the most useful aspects of HRV is its ability to quantify progress in a way that subjective feeling often cannot. Someone might feel tired or anxious without knowing exactly why, but a low HRV can point to autonomic imbalance, prompting interventions like breath regulation, rest, or even cold exposure to restore equilibrium. In this way, HRV bridges the gap between intuition and data, allowing individuals to track the physiological outcomes of their behavioral choices. Because HRV is sensitive to both physical and emotional inputs, it reflects not just fitness or recovery, but also mental and emotional well-being. People who regularly meditate, breathe slowly, engage in cold therapy, and maintain consistent sleep patterns often see meaningful increases in HRV, indicating a more responsive and resilient nervous system. The combination of cold exposure and HRV monitoring creates a feedback loop that is uniquely powerful. Deliberate cold exposure acts as a stimulus that strengthens the nervous system, while HRV provides the data needed to measure whether that stimulus is helping or hindering. Together, they offer a precise and practical way to improve stress tolerance, emotional regulation, and overall physiological resilience. Cold exposure, when done safely and consistently, conditions the body to endure stress without overreacting, while HRV tracking offers the insight to fine-tune this practice and understand its broader impacts. These tools are also accessible. Cold exposure requires nothing more than cold water, and HRV can now be measured with wearable devices that provide minute-by-minute updates on nervous system performance. This democratization of physiological data empowers individuals to take charge of their own nervous system health, moving from passive recipients of stress to active participants in their own resilience and recovery. The physiological changes induced by cold exposure also extend beyond the nervous system. Cold can reduce systemic inflammation, boost immune function, increase mitochondrial efficiency, and elevate levels of norepinephrine and dopamine, neurochemicals associated with alertness, focus, and improved mood. These changes are not just transient spikes. With consistent exposure, the body recalibrates its baseline stress response, allowing for greater mental toughness and emotional balance. These benefits also reflect in HRV trends over time, where consistent cold exposure can lead to measurable improvements in baseline HRV scores. This suggests a broader shift in how the body perceives and responds to stressors of all kinds, not just cold. The more adaptive the body becomes to these controlled stressors, the more capable it is of navigating real-world challenges with calmness and composure. Breathing plays a pivotal role in both cold exposure and HRV regulation. In the moment of entering cold water, the initial gasp reflex is a sign of sympathetic dominance, but by consciously slowing the breath and extending the exhale, the parasympathetic nervous system can be engaged even in the midst of a highly stressful stimulus. This capacity to regulate breath in a moment of discomfort is a direct training of vagal tone and enhances the control one has over their own autonomic responses. When practiced regularly, this breath control becomes habitual, allowing for better emotional regulation in all areas of life. The same breath patterns that calm the body in an ice bath are the patterns that can calm the mind in an argument, a high-pressure meeting, or a moment of fear or uncertainty. Cold exposure simply makes the practice visceral, real, and embodied. HRV also reflects how well these breath-based adaptations are taking place. As individuals learn to shift their breathing, adjust their mental framing of discomfort, and remain centered under pressure, their HRV scores respond in real time. This feedback creates a reinforcing loop. Cold exposure teaches the body how to adapt to stress, breath controls that adaptation, and HRV confirms that progress is being made. Over time, the entire system becomes more fluid and adaptive. Instead of reacting to stress with panic or shutdown, the nervous system learns to engage, respond, recover, and re-engage. This dynamic flexibility is at the core of all high-performance states, whether in athletics, leadership, relationships, or creative pursuits. Cold exposure and heart rate variability are not merely trendy wellness practices, but deeply grounded in the science of autonomic nervous system regulation and human adaptation. When the body is suddenly introduced to a cold environment, whether through an ice bath, a cold shower, or a plunge into cold water, it reacts by activating the sympathetic nervous system, which is responsible for initiating the body's fight or flight response. This response includes a rapid increase in heart rate, constriction of blood vessels, and the release of stress hormones like norepinephrine. The immediate reaction is one of discomfort, but that discomfort is precisely what begins the training process. The nervous system learns to handle stress more effectively over time, gradually becoming more efficient at shifting from sympathetic arousal to parasympathetic recovery. This balance between stress and relaxation is what creates long-term resilience and enhanced capacity to deal with both internal and external challenges. The cold becomes a tool not for punishment, but for precision training of the body's core regulatory systems. The repeated exposure to cold enhances the responsiveness of the vagus nerve, which plays a vital role in parasympathetic activity. This nerve acts as the primary communicator between the brain and vital organs, sending information about the body's state back to the central command center. Stimulating it through cold exposure forces the body to practice its recovery processes. Initially, the cold causes stress, breathing quickens, the heart races, the body tightens, but with controlled breathwork and mindful exposure, the parasympathetic system begins to activate more rapidly. This means that the body doesn't remain stuck in a hyperaroused state, but instead learns to come down from that stress more quickly and efficiently. Over time, this neural conditioning results in improved regulation of emotional reactivity, greater clarity under pressure, and a more adaptable stress response cycle. Cold exposure teaches the system that stress is not always a threat. It can be a form of stimulation that, when handled correctly, leads to growth and increased capacity. At the physiological level, cold exposure increases mitochondrial function, leading to better cellular energy production and improved metabolic efficiency. It stimulates the release of brown adipose tissue, which burns energy to generate heat and contributes to improved insulin sensitivity and body composition. Neurochemically, cold exposure elevates levels of dopamine, the neurotransmitter associated with motivation, pleasure, and attention. Unlike the rapid spikes followed by crashes that result from synthetic stimulation or poor habits, the dopamine elevation from cold exposure is gradual and sustained, leading to longer lasting effects on mood, drive, and alertness. In tandem, the cold reduces systemic inflammation by suppressing pro-inflammatory cytokines and improving circulation. This means that cold exposure is not just beneficial for mental toughness or energy, it supports deeper physiological healing and long-term health regulation. Heart rate variability, on the other hand, acts as a window into the internal workings of the nervous system. It reflects the beat-to-beat variation in the time interval between heart contractions, and while a high HRV indicates a well-regulated nervous system with a strong vagal tone, a low HRV often points to chronic stress, overtraining, inflammation, or emotional dysregulation. It is not about how fast or slow the heart beats, but how adaptive the heart is to constantly changing internal and external environments. A flexible heart rhythm, one that can speed up or slow down in response to breathing, emotion, or physical challenge, is indicative of a nervous system that can shift gears appropriately. HRV becomes a real-time indicator of how the brain and body are working together. Unlike many subjective assessments of stress or wellness, HRV gives direct, objective feedback that can be used to track trends, understand recovery needs, and fine-tune health interventions. The relationship between cold exposure and HRV is reciprocal. Regular cold exposure increases HRV over time by improving the body's capacity to transition smoothly between arousal and calm. It strengthens the parasympathetic system, allowing for faster heart rate recovery after stress and greater adaptability in day-to-day life. Meanwhile, monitoring HRV provides valuable information about how well the body is responding to cold exposure. It helps individuals determine whether their current routines are building resilience or whether they might be overtaxing their system without sufficient recovery. This dual practice of applying a physical stimulus and measuring its nervous system impact allows for individualized optimization of stress, performance, and recovery cycles. The awareness of how stressors like cold affect HRV patterns helps users make informed decisions, such as when to intensify exposure, when to pull back, or how to structure complementary practices like breathwork, sleep, and nutrition. HRV is also influenced by respiratory control, and breath becomes an active tool in both the application of cold and the cultivation of nervous system balance. Deliberate control of the breath, especially in stressful or uncomfortable moments, teaches the nervous system that it is safe. In the case of cold exposure, the initial gasp and rapid breathing are natural reactions, but by bringing conscious awareness to the breath, slowing the inhalation, lengthening the exhalation, one activates the vagus nerve and signals the body to enter a recovery state. This regulation, practiced consistently, translates into everyday life. The same breath that calms the body in an ice bath can calm the mind during a conflict, an unexpected challenge, or a period of emotional upheaval. Breath becomes the bridge between stimulus and response, between sensation and interpretation, and it reinforces the neurophysiological shifts that cold exposure initiates. The consistent application of these two tools, cold exposure and HRV monitoring, also has profound effects on mental and emotional capacity. Individuals who practice regular cold immersion often report increased confidence, reduced reactivity, and a greater sense of self-control. These psychological benefits are not abstract. They arise from measurable changes in brain chemistry, nervous system tone, and cognitive focus. Cold exposure acts as a mental reset button, pulling the individual fully into the present moment, stripping away distractions and demanding presence. It becomes a form of exposure therapy for the nervous system, helping people learn how to sit with discomfort, how to override the impulse to flee, and how to stay regulated under pressure. Over time, this repatterning of the stress response leads to greater equanimity in other areas of life, making it easier to handle everything from interpersonal stress to physical performance challenges. Tracking HRV throughout this process offers constant feedback. On days when HRV is high, one may be primed for intensity, whether in training, focus, or emotional labor. On days when HRV is low, the body is asking for restoration. This nuanced understanding of internal readiness allows individuals to stop operating blindly and start training, working, and recovering with precision. The integration of cold exposure and HRV creates a closed-loop system, one that not only builds capacity, but also measures it. It teaches the nervous system that it is capable of withstanding challenge, recovering from it, and ultimately growing stronger because of it. Cold becomes a catalyst for nervous system adaptation, and HRV becomes the mirror reflecting that transformation. This partnership of stimulus and feedback refines the nervous system like few other tools can, grounding abstract concepts like resilience, discipline, and focus in tangible, trackable biological change.